When I first saw the first light image from Kepler, my reaction was, wow, there are a lot of stars in this image. We are covering 100 square degrees of sky, and there are literally millions of stars in that field. So the image just glitters with stars. It was impressive. The habitable zone is the distance from a star where the temperature of the planet is amenable to water being liquid on the surface. So it's like the temperature we have on Earth. If you're too close to the star, it's too hot, the oceans boil away, you're just left with a hot rock. If you're too far away from the star, it's too cold, everything freezes out, you've got an ice world. So we're interested in this Goldilocks zone where liquid water can be present. We call that the habitable zone. If we find an Earth in the habitable zone, I'm going to pop a bottle of champagne and celebrate. That's what I'm going to do personally. I think a lot of others will be joining me. One of the challenges, though, is we need to make sure that we're really looking at an Earth-like planet. There are a lot of effects out there that can masquerade like transiting planets, and so we have a very rigorous follow-up observing program to make sure that we don't have a false detection and that we're looking at something else. But once we have that confirmation that we found an Earth-like planet orbiting in the habitable zone, we will know that we are not the only world that's capable of having liquid water on the surface. And I'm going to celebrate. Kepler was not designed to take pretty pictures. Kepler was designed to allow us to measure the brightness of individual stars in the field, originally 170,000 of them, later on down to about 100,000. We want to be able, every 30 minutes, to be able to measure the brightness of stars. So we didn't design a telescope to take pretty pictures. We designed a telescope to make these specific, very accurate brightness measurements.
It's a great milestone. The first light shows us that all the 84 channels, all the detectors are working well. We're seeing millions of stars in our field of view. And a few more tweaks, some calibration, and we'll be ready to start the search for planets. There are something like 30 people in the United States. There are a couple of hundred in Europe, all who want this data desperately, because they know we're going to be making tremendous discoveries in a lot of different scientific areas. Areas about finding planets, areas about understanding the insides, the structure of stars. How do they evolve? We will actually watch a star live. It will change while we actually watch. So everybody, every team member is extremely excited.
22 seconds.
We
20
have a
seconds.
green board here in the Mission Director Center.
15
15 seconds.
13 seconds. Green board.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2. Engine start. 1, 0. And liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Vernier engine chamber pressures are building. Groundlit solid motors are building in chamber pressure. Increasing at this time. Pressure's looking good. 1 second into the flight. Recovering from the initial launch transients. Passing 34 seconds. Mach 1. Vehicle's now going supersonic. Motor chamber pressure is beginning to trail off as we're passing 45 seconds. Engine chamber pressure, good steady state value. Symmetrical burn on the groundlit solids. Coming up 55 seconds.
And we have a sequencer on channel 1. Sequencer.
Standing by for burnout.
Give me a liftoff time. 03.
Burning out of the solids.
49.
And for separation.
4.65.
We see separation.
7.465.
And we have ignition of the airlit solid motors.